This conference will now be recorded.
Hello everyone. Today's topics will be quantum numbers. Though there are 4 quantum numbers, 2 of them already discussed in last class, and today we'll discuss 2 more quantum numbers. And after that, there will be probability distribution in an orbital, radial distribution function, radial and angular nodes in p and d orbital, shapes of orbital, and related problems. So, principal quantum number and azimuthal quantum number. These 2 quantum numbers we have already seen. This is number 3, that is magnetic quantum number, which is denoted by m subscript L. Sometimes it is simply expressed as only m, ml or m. So what is the significance of this number? It gives information about the number of preferred orientation of the electrons in subshell, and each of these orientation, based on each of these orientation, there will be different orbital. So from azimuthal quantum number, we have seen that under a particular principal quantum number, how many subshells are possible. Now these subshells, there may be different types of orientation. So depending on these different types of orientation, we can have different orbital. So that is why we have now this third quantum number, which is magnetic quantum number. So this will give us information about the preferred orientation of the subshells. So for any subshell, we know it is denoted by small l. So for any subshell, how many orientations are possible? That is actually the possible numbers of ml. So 12 plus 1, these are the possible values of ml. If you know the value of small l, suppose for s orbital it is 0. So it is 2 into 0 plus 1, that means it is simply 1. So ml value will be 1. Similarly, you can put L equal to 2, L equal to 1, and you can get the corresponding number of ml. That is how many possible orientations. That number you will get from 12 plus 1. Fine. So if 12 plus 1, it is the possible values of ml, and each of these is basically corresponding to an orbital. So for each orbital, if you consider 2 electrons per orbital, because that is the maximum capacity, and total number of orbitals 12 plus 1. So if you want to know the maximum number of electrons that can be accommodated in a given subshell, that you can get, simply multiply 12 plus 1 with 2, because per orbital there will be 2 electrons. So if you want to get total number of electrons that we can accommodate in all these 12 plus 1, so obviously it must be multiplied by 2. Okay, and these ml values, when you will actually see all the values, you will see that it is basically ranging from minus L to plus 1. Now what it means, suppose L is 1, so in that case 12 plus 1, it should be 2 into 1 plus 1, that means it is 3. Now if it is 3, that means total ml values possible, total 3. So how it will range from minus L to plus 1? Sorry, it is L, it is not 1. Minus L to plus L. So L is 1 and total possibility is 3. So it will start from minus 1, because minus 1 is basically minus L. The next one is just simply add plus 1. So when you add plus 1 with minus 1, it will give you 0. Next again add plus 1. So 0 and plus 1, it is basically plus 1. Now you have already reached the maximum capacity, because the maximum capacity, as it is mentioned here, it is minus L up to plus L. So you have already reached the capacity, and see total 3 values which you have already obtained here. So in this way you can also find for L equal to 2, L equal to 3. So suppose if it is L equal to 2, then 12 plus 1, it will be 2 into 2 plus 1, that means total 5 possibilities. Now if it is 5 possibilities, and we will try to see the range from minus L up to plus L. So start from minus 2 because minus L, that means minus 2 should be the first possibility. Now from minus 2, the next value how you will get, simply add plus 1. So minus 2 plus 1, it is basically minus 1. Then again add plus 1 with minus 1, it will give you 0. Again add plus 1 with 0, you will get plus 1. Then add again plus 1, it will be plus 2. Now you have already reached the limit, which is plus L. So these are the two limits. Okay. So how many you are getting? You are getting total 5. So this is actually 12 plus 1, the possible values of ML. So in this way, you can understand that how many integral values you can get starting from minus L to plus 1, and it will always be passing through 0. So here we will see these pictures for p orbital and d. So for p, as we have seen, it is 3 possibilities: ml, minus 1, 0, and plus 1. So these 3 basically denoted by px, py, and pz. And don't think that it is only true for 2 pz, 2 px, 2 py. No, it is also true for 3 or 4, because here we have taken particularly 2 value, that is principal quantum number is 2, but it is also same thing you can get when it is 3px, 3py, 3pz, because whatever it is, whether you take 2p, 3p, or 4p, one thing is common, it is always p, and you just have to focus what is the L value. Here L is 1 for 2p, 3p, 4p, because just principal quantum number is changing, but azimuthal quantum number is not changing. That means p is same. So whether it is 3p, 2p, or 4p, you will always get 3 possibilities. One is minus 1 ml value, then ml value 0, and ml value 1. So here you can see we have chosen principal quantum number 2. You can choose any. Only difference will be here the lobes that you are seeing. In case of 3p or 4p, the size will be high. So here we are just interested in the preferred orientation, and here total 3 preferred orientation: 1, 2, 3. One is minus n, minus 1, then 0, and plus 1. Okay. So here you can see. Now if you are thinking why the lobes are so, that is why the shapes are so. Now the shapes, if you want to know, that is completely different thing. We will discuss it later. Right now we are just seeing that how many ml values are possible. Okay, just don't just focus on the lobes and shapes, that will be discussed differently. So here we have this p orbital 2px, which is along x-axis. So that is why these two lobes, you can see it is along x-axis. Next, when it is py, it is along y-axis, and it is the third one is along z-axis. Now the second picture, as we know, when L is equal to 2, there are total 5 possibilities. And what are those 5 possibilities? Minus 2, minus 1, 0, plus 1, and plus 2. So when it is ml minus 2, here we have this orbital 3d x square minus y square. Now the names are so that you have to memorize. Then when it is dx square y square, see here the lobes are directly on the axis of x and y. So these lobes are on x axis, these two lobes are on y axis. Then for 3dz square, here it is complete, it looks different, right? It is along z axis, and there is a donut type of shape. Then the third one is 3dxy. Now 3dxy, 3dxz, 3dyz, they will be in the plane, which is, you can understand from the superscript. When it is xy, it will be in the xy plane. So this is xy plane, right? When it is xz, it will be xz plane, because this is x-axis, this is z-axis. So this plane is basically xz plane, and here the lobes are in between the axes, which is not same as 3d x square minus y square. Where the lobes are directly on the axis, here the lobes are in between the axes. So 3dx The lobes are between z and x-axis, and it is on xz plane. That is important. And for yz, now this is z-axis, this is y-axis. So now it is in zy plane like this. Fine. So in this way, we can get total 5 ml values. So here it is shown for 3D, but it is also true for 4D or 5D like this. Okay. So for S, here only one possibility because L value is 1. When it is P, L is 0 for S. For P it is 1. For D it is 2. For F it is 3. So when it is 3, obviously 12 plus 1 will be 2 into 3 plus 1. That means 2 into 3, 6, 6 plus 1, 7. Total 7 possibilities are there. So starting from -3, then -2, then -1, it is ending at 3. Okay. Now, if you want to know what is the experimental justification for this quantum number, it is observed that when the spectral lines are observed in magnetic field, there is some splitting observed. That means when it is in presence of magnetic field, there is something happening. Okay. So in a particular magnetic field, there will be some change in the orientation of the orbital, and it is already observed that this splitting of spectral lines that we get in magnetic field, it is because of this preferred orientation. So depending on the preferred, how many preferred orientation you are getting, there will be, accordingly you can explain the splitting of spectral lines under magnetic field. And this process, this incident is known as Zeeman effect. So basically you can say in a very simple way, you can explain Zeeman effect with this magnetic quantum number. So this effect, that is Zeeman effect, it is basically providing us the experimental justification for this third quantum number. One important application of this ML is you can get angular momentum value, that is the magnitude of angular momentum you can determine from this L value. Okay, and if you want to know its direction, that you can get from ML. Okay, so we know that how to calculate angular momentum by using L. It is root over L into L plus 1 h by 2 pi. That formula you have to use. But if you want to know what is the direction, that is actually given by ML. Fine. So that is all about this third quantum number. Now the fourth quantum number. We have already seen it that the first three quantum numbers, that is principal, azimuthal, magnetic, these three quantum numbers basically you get from Schrodinger equation. But the fourth quantum number, that is not directly related to them. Okay, so these three quantum numbers, why we need this fourth quantum number, that we have to understand first. So suppose you don't have any fourth quantum number, this is the fourth quantum number, but suppose we do not have that, what will happen? The three quantum numbers that we have already mentioned, they actually work well if you are describing electron orbital. But there are some experiments from which we can see that these three quantum numbers are not enough for some other observed results explanation. So if you want to explain those experiments, basically these three are not enough. So we need some extra quantum number, which is spin quantum number. And this is denoted by ms or sometimes simply by S. When hydrogen line spectra, that is for hydrogen like system, the line spectra are examined at extremely high resolution. Suppose it depends on resolution. When it is very high resolution, you can get some detail of this spectra, right? So when it is under high resolution, it is observed that some lines are actually not single lines. These lines are actually closely spaced lines. So suppose I am drawing here a line, but if it is under high resolution, you will see that as if it is collection of some closely spaced lines, which are known as fine structure of the spectrum. Now, why we are observing this? It means if it is not single line, when it is not high resolution, if you are thinking that there is only one line, that means only one energy, that is as if there is one energy level is involved and for which we are getting this line. This is lower energy level to higher energy level. But when you are getting a bunch of lines that are closely spaced to each other, it means there will be some more energy level. So that is why you are getting more lines. Now, where from these more energy levels are coming, that we can explain by spin quantum number. So it means that there are additional small differences in energies of electrons, and it is very small difference energy level, because that is the reason the lines are so closed. They are not far from each other. But still we are getting some additional small difference in energies of electrons, even though they are located in same orbital. Because you have already seen in case of ML, suppose just take a p orbital. So there is -1, 0, +1. And in each orbital there is 2 electrons. I am writing electron like this. Fine. But within, that means, what means? These 2 electrons, they should give similar type of line spectra, because all the quantum numbers for these 2 electrons are same. Principal quantum number same, L is same, ML is same, because they are in the same -1 subshell. But you are getting some different results. That is, for these 2 electrons, you are getting different results. That means there is some difference between these 2 electrons. They are not completely alike. So what is the difference? So I should not write this electron like this. Basically, they should be written with arrows, and arrows are like this. So see, one is arrow, it is upper side, this is lower. So it is always written in this way. Now what it means, this upper arrow, lower arrow, it means basically 2 different spin quantum number. Okay, so as there is small difference in energies of electrons, even though they are located in the same orbital, so these 2 electrons are in same orbital, but still there is some small difference in energy. So it proves that there must be, this observation led to a 4th quantum number, which is spin quantum number. And spin quantum number is basically +1 and +half and -half. Now why this, for one arrow it is +half, another one it is -half. Okay, so 2 possibilities are there. Now why it is behaving like this, why we are also calling it spin quantum number? So it is called spin because electron is a charged body, right? And it revolves surrounding nucleus. So that is one of its motion. But it also rotates on its own axis. Fine. So when a charged body rotating on its own axis, it will behave like a tiny magnet. So a tiny rotating object with an angular momentum, though this rotation cannot be observed in terms of spatial coordinate, because it is not changing with respect to spatial coordinate, it is rotating on its own axis. Okay, so suppose if I'm drawing, suppose this is an electron, it has its own axis, and nucleus is somewhere here, positive sign I'm drawing, and we know that electron is rotating like this, revolving surrounding nucleus, but it is also rotating in its own axis. So I'm talking about that, not this one. I'm talking about this rotation on its own axis. Okay, just focus on that. So this rotation you cannot observe in terms of spatial coordinate, but still it is present, and it is basically leading to this spin quantum number. Okay, so corresponding to whether it is clockwise spinning of the electron or anti-clockwise spinning of the electron, maximum 2 values are possible. So see, here one electron, you can also draw like this, or you can draw in this way. So one will be treated as ms value +half, and another one downward, that will be treated as -half. Okay, so whether it is clockwise or anti-clockwise, based on that 2 values are possible. So one is denoted by upper arrow, another one is downward. Okay, So this is all about spin quantum number. So it is not, we are not getting it directly from Schrodinger equation. It is obtained different. Fine. Now all these 4 quantum numbers, as we have discussed, we will see them in a single table. So principal quantum number denoted by small n, and allowed values are simple integer, but it doesn't start with 0. It has to be from 1 and up to infinity. And what is its physical meaning, that is significance? It is basically denoting the shell with the primary energy level, the general region for the value of energy for an electron on the orbital. Okay, so if you know n, basically you can understand what will be its energy depending on it is level n1 or n equal to 2, that is n2. Depending on that, you can understand how the energy is changing. Okay, so that is why for the value of energy of an electron, if you want to get information from that you can get from this. So if you know what is principal quantum number, you will be able to understand what is the corresponding energy for that electron. Now the second one is azimuthal quantum number or angular momentum quantum number, denoted by small l. And L values, it start from 0, then greater than equal to, and it is ending at n minus 1. So these are the maximum possibilities. Okay, so suppose if L is equal to 2, it will start from 0, next value will be plus 1, next value will be, no, next value is not possible. Why? Because the next one is actually 2, but maximum limit is n minus 1, and in this case you have chosen L is 2. So when n is 2. So when n is 2, L values will be 0 and 1, because the next one is 2. But when you are choosing next L value as 2, it is not possible because it is directly equal to 2, because the final limit it should be n minus 1. So when n is 2, obviously n minus 1 is, it should be 1. So that is why when principal quantum number is 2, maximum values of azimuthal quantum number is 0 and 1. Fine. What is the physical meaning? It will give you basically the subshell, and also you'll be able to know the shape of the orbital. Remember in last class, suppose you know what is L. If it is 0, its shape is S orbital. If it is 1, it is having p orbital. So you know the corresponding shape. So that is why it will give you the idea of shape. Now the third and fourth, magnetic and spin, denoted by ml or ms, sometimes also denoted by m or s. So ml values, possible values are starting from minus L up to plus L. But you can also consider this formula 12 plus 1. So it will give you the all possible ml values. And what it says significance? Significance is you can understand the preferred orientation of the orbital. So when ml values you are getting 3, 2l plus 1, suppose 2l plus 1 you are getting 3. That means total 3 preferred orientations will be there. And the spin quantum number, plus up and minus up, it denotes the direction of intrinsic quantum spinning of the electron. Okay, it is intrinsic. It is not that it is revolving the nucleus, but it is rotating on its, spinning on its own axis. Fine. So that is all about 4 quantum numbers. Next topic. Okay, we have some problems. So it is asking that which of the following set of quantum number is not permitted. Here in options A, B, C, D, you can see n value, L value, M value, S. So all the 4 quantum numbers are given: principal, azimuthal, magnetic, and spin. But it is asking which set is not possible, that is not allowed. That we have to understand. A, B, C, D. Now in all cases, principal quantum number is 3, but others are not same. Now if you remember this table, this is actually correct answer, but why it is so we will see. Just remember this table: when principal quantum number n possible values of L, it start from 0 up to n minus 1. Now if it is true, and when n is equal to 3, because in all options it is 3, obviously L value cannot be equal to 3. So n equal to L, it is not possible, and that you can see in option C. So that is why, based on this, that is, I'm just trying to say this much information is enough to choose the correct option. Even you don't have to look at the other two values. So N3, L3 both are same, it is never possible. And other values are possible, that is -3, -half, because when L is 3, obviously M values can be -3, -2, 0, all these are possible. So that is fine, because ML value, it starts from -L. So if L is 3, it can start from -3. But the problem is when n is 3, principal quantum number, L cannot be 3. Now here, if you are interested, you can we can also check what is the corresponding orbital. So suppose n is 3, L is 2. Now L2 means what? It is d orbital. So it must be 3d. Okay. So it is basically 3d orbital. And in 3d, if you see how we write it, 3d total 5. Start from -2, +1, 0. So -2, -1, 0, +1, +2. And here ml value is 0. So the placement of the electron and S is plus up. So it can be like this. Fine. Now same thing you can also do for option B. So option B, N is 3, L is 2, M is -2. So now the electron should be here. I'm drawing in the same picture, and it is also plus up. Now N is 3, L is 0. L0 means it is 3s. So option D is basically 3s electron, and where only one M value possible, and electron is downward here. So all these are possible, but C, option C is not possible. So this should be the correct option, because it is asking which quantum number set not permitted. Next question. The number of orbitals associated with quantum number n is 5. So here only principal quantum number given and spin quantum number given, which is plus up. Based on this information, you have to check how many number of orbitals possible having this value of principal quantum number and spin quantum number. Now when principal quantum number is 5, first you have to check how many L values are possible. So L value, it should range from 0 up to n minus 1, that means up to 5 minus 1. So it is basically 0 to 4. Now when it is 0, it is S, then 1, then 2, then 3, then 4. So it will start from S, then P, then D, then F, and then G. All these azimuthal quantum numbers are possible. Okay, so step by step we will see. When n is 5, L total, it will be 4. So starting from, so why it is written so? Because these are the possibilities: 0, 1, 2, and 3. So these are the 4 possibilities. Now 0, 1, 2, 3 means it is S, this is P, this is D, this is F. Okay. Possible subshells for N5, sorry, G will also be there. So it is not like this. Just ignore this information. When n is equal to 5, possible subshells for n equal to 5 will be S, P, D, F, G, because it starts from 0 and it ends at 4. ncert 4 means it is ending at n minus 4. So that is why all these are possibilities. Now we know that when it is s, how many electrons you can place in s? There is only one magnetic quantum number. That means maximum electron you place, it is 1. Now for p, there are total 3 ml. That means in each there is 2. So maximum possibilities, there is actually 3 into 2. But as we have to take only one spin, it is not that you can take both plus half and minus half. You have to choose only one. So that is why when it is s, basically there are total 2 electron possibility. But we will not choose 2. We will choose only one, because among these 2 possibilities, you can take only this. Similarly for p, there are actually 6 possibilities like this. But you have to choose only this first one, because you are restricted to the value of spin quantum number plus half. So that is the reason for s, p, d, f, g. Basically, the electrons that you can place, it will be 1, 3, 5, 7, 9. Or you can also think like this, that the number of orbitals possible for each of these 5s, 5p, it is 1, 3, 5, 7. And how we will calculate this? This is very simple, because when it is s, it is L value is 0. Okay, so 12 plus 1 for 5s, it is basically 1. Now 12 plus 1 for 5p, it is actually not important 5 or 4p. It is p, that means azimuthal quantum number is 1. So 12 plus 1 will be 3. Then for d orbital, L value is 2. So total possibility is 5. So in this way, for F it is 7, for G it is 9. So these are the number of orbitals, and maximum number of electrons you can place is number of orbitals into 2. So it should be, if it is simply asking with n equal to 5, how many electrons you can place, then it will be, you in each value you have to multiply with 2. But here it is basically asking the number of orbitals associated with n equal to 5, as well as you have to maintain this condition. So that is the reason just one electron we can choose, and that is why the answer will be 1, 3, 5, 7, 9 for each of these 5s, 5p, 5d, 5f, 5g. Now if you add all these numbers, summing up, that is 1 plus 3 plus 5 plus 7 plus 9. It will give you 25. Similarly, here it is asking number of orbitals associated with this quantum number. But if it is asking like this number of electrons associated with this quantum, then also answer will be same. So here correct option is option B. Okay. Consider the following statement. How many statements we have? We have total 5 statements, A, B, C, D, E. Now after that is reading all these 5 sentences, next you have to check how many of these 5 are actually correct. 4 options are there. First option 3 statement, second option 4 statement, third option 3, fourth option again 4 statement. So one by one we have to check all these statements. The first statement is saying principal quantum number small n. We know it is principal quantum number denoted by n, that is fine. And here it is mentioned positive integer with values 1 to 3. Now this is absolutely correct. This is true. Next statement is, now based on this information you cannot choose any option, because in all the options you have the statement A. So we have to move further. Come to the second statement. Second statement is saying that azimuthal quantum number for a given n, that is for a given principal quantum number, it can have values starting from 0 up to n. But what we know, L value it starts from 0 and it ends at n minus 1. But here it is mentioned it is n. So this is not correct. This is wrong. So the options should not contain statement B. So based on this, you can cancel option 1, option 4. Now the next statement, magnetic orbital quantum number ml for a particular value of azimuthal quantum number, it has 12 plus. Now this is true. So option, not option, statement C must be present. Okay. Now in both option 2 and 3, statement C is there. So you have to move next. Plus half and minus half are the two possible orientations of electron spin. This is also true, right? And the third option, now this is also true, means again you cannot choose between 2 and 3. You also have to check E. Last statement is saying azimuthal quantum number is 5 and there will be a total of 9 orbitals. But what we know, how many orbitals for this value of L, that you can get from applying this formula. So 12 plus 1, it is basically 2 into 5 plus 1. So 2 into 5 plus 1, it is basically 11. So this statement is not correct. So from all this discussion, what we can conclude, it is not option 2, it is option 3 that should be correct. So the first statement, number of values, it is true. Second statement is basically false, but here it is already corrected. And it is false. This is also false. So it is basically TF, TTF. Number of values of ML, 12 plus 1. So that information is correct, given in third statement. Fourth statement is also correct. And the last statement, it is basically 11. The correct information is given here. It is not 9. So option 3 should be the correct option. Right? So after discussion of these problems that are based on quantum numbers, next topic is probable distribution in an orbit. So when we have discussed probably in the last class the Schrodinger equation and how we get its solution, what is the significance of the solution psi, that we have seen. And there we have also seen the information that this wave function psi itself has no physical meaning. But when you take square of it, it will basically give you the probability of finding the electron in a particular region. And that particular region we have mentioned is like this: dx, that is three coordinate you have to consider, x, y, z. So if you take a small part of x, dx, then small part of y-axis, dy, and dz. So when you multiply all these three, basically you get a very small volume, and that is, we call it unit volume. So chi square, it is basically it is called probability density. What is probability density? It is the probability per unit volume. You can consider unit volume, these dx, dy, dz, or you can, in generally we can write it as dv. That is a small volume element or small unit volume. So when you this is probability density, probability per unit volume. So that is why it is density per unit volume. Remember, what is the definition of normal density? Density, we know it is mass per unit volume. Similarly, when it is probability density, it is probability per unit volume. And if you multiply with this chi square, here mod sign is given, but don't be confused by that. Mod sign is given, even if you don't write it, it is fine, because whether there is a negative sign for wave function, when you take square, it doesn't matter, it will always be positive. So probability of finding the electron in unit volume, it is always positive. So mod sign, even if it is not there, it is okay. So this chi square, when you multiply with it a small volume, which is called volume element, which is nothing but this dv or dx, dy, dz, then you will get probability of finding the electron in that particular volume. Okay, and if you are not multiplying it, if it is simply chi square, it is probability density. Now why we are specifying this small volume element with this chi square? The reason behind it is that it can vary, that is chi square can vary from one region to another in space if the space is very large. But if you consider a small volume element, then you can assume as if the value of chi square, that is the probability of finding the electron in that small volume, it is constant. It will not change because the volume is very small. But suppose if it is, you are considering a large region, obviously chi square will change its value. Okay, so that is why when we are multiplying with this chi square a small volume element, it will give you the probability of finding the electron in that particular volume. And if it is very small volume, obviously the probability of finding the electron, that will be constant. The total probability of finding the electron in a given volume, that is, suppose now the given volume is large, how we will get it? You know what is the total, that is the, not total, you know what is probability of finding the electron in a small volume. But how we will get the total probability? So all this small volume, suppose you have chi square dv1, chi square dv2, chi square dv3. So if you add all this, if you sum all these products of chi square and the corresponding volume element, then you can get the total probability of finding the electron in a given volume, which is large. So in this way, it is possible to get the probable distribution of an electron in an orbital. So these are the significance of this term, probability density. Some more information for this chi, which is basically Schrodinger, we get from Schrodinger wave equation. This is basically the solution of Schrodinger wave equation for hydrogen-like system. Now, until now we have said that the solution is chi, but this chi is basically, it is a function of spherical polar coordinate. Spherical polar coordinates are r, theta, and chi. Now this wave function, which is basically function of r, theta, and phi. Basically r is distance, theta and chi, these two are angle. So chi is function of this. Now chi can be written as a product of two different parts. What is this two different part? See, all these are very detailed and very complex, higher mathematics, that is physics mainly, that are involved. But in our syllabus, this much I'm trying to present is as simpler way as possible, okay, which is necessary for you, because if we want to go into the details, that will be completely irrelevant. It is not in syllabus. So we will just take that much information which will help us to solve the problem and understand this topic. Okay, so here the first part is r, which is function of r, capital R, function of r. This is known as radial component, and it depends on the distance from the nucleus. And also remember this radial part, it is dependent on principal quantum number and azimuthal quantum. And the second part, this one, it is angular part. And angular part is dependent on which quantum number? Azimuthal and ML, magnetic quantum number. It is not dependent on principal quantum. So chi can be expressed as radial component and angular component. So why we are dividing into two components? Gradually you will understand that. So from angular component, probably will not get time in today's class. In the next class we can see that angular component is basically helping us to get the shape of different orbitals. Why S is spherical, why P is having some dumbbell shape, there are two lobes. So all these informations basically we get from this angular component. Okay, but first we will discuss in detail the radial part. So radial distribution function. It is important for us to know that how this chi square varies with distance from the nucleus. Not only variation with distance from nucleus, but also what is its direction from the nucleus. Now the information related to direction is present in angular distribution of the probability, but how it varies with distance from the nucleus, that is related to radial distribution of the probability. So first we'll focus on this, and mainly our focus will be on this only. The second one, that is the direction, angular distribution of probability. Details, it is not there in our syllabus, but radial distribution function, there is some specific graphs that how chi-square changes with distance r. Based on these problems are also there. So to solve those problems, we have to understand this radial distribution function, and that is basically solely based on the radial component, not the angular component. The angular component is, it will give you the idea about the shapes. But right now we are talking about radial distribution function, which is completely related to the radial part. That is the radial component. You have seen in the previous slide there are two components, radial component, angular component. So this is based on radial component. Here we have some terms that we have to know. We have already heard this term, probability density. Now, in the previous slide, which is denoted by chi-square. But when I'm saying radial probability density, it is basically r square, which is function of small r. So it is square of radial wave function. That is, the radial component square is called radial probability density. And what is the term radial probability? To understand radial probability, first look at this picture. So this is nucleus, and the distance is r for this. If you consider this circle, actually it is not circle, it is basically sphere. You have to imagine it in 3 dimensions, but as it is drawn on screen, it seems 2 dimensional, but imagine it as if it is 3 dimensional. So this is radius, and if I am saying this radius is r1, suppose this is r1, so r1 minus r is dr. Now dr, as it is d and r, dr means it is a very small distance, so this distance is very small. So this is dr, this is r. Now if you apply the formula of circumference, which is 4 pi r square, so circumference for this, it is 4 pi r square. But if you multiply with this 4 pi r square, if you multiply with this dr square, basically you will get the volume of the spherical shell. Now what it means, volume of spherical shell, it is basically the volume for this crisscrossed region. Don't think it is the volume of this whole sphere. No, if you simply consider this radius, there will be a sphere. If you consider the radius r1, there is the sphere. But suppose you are just taking the volume, that is the sphere which you get from r1 radius and the sphere that you get from r radius, just you have to subtract it. Then only you can get the volume which is only in the crisscrossed region. And if you want to get the volume, you have to multiply this distance dr with the circumference of the smaller sphere. And the circumference formula is 4 pi r square, and it is multiplied with dr, which will give you the volume of this spherical shell, that is the marked region. So radial probability is basically the probability of finding the electron within the spherical shell enclosed between a sphere of radius r plus dr, which is nothing but r1, as I have mentioned, and the sphere of radius. So it is in between r plus dr sphere and the sphere of radius r. In between this space, whatever volume is there, the probability of finding the electron in that volume, that is known as radial probability density. And radial probability. So how you can get this radial probability? To get it, you have to multiply volume of the spherical shell with radial probability density. Now radial probability density, we have seen it is already in the first line, it is r square, and you have to multiply volume of spherical shell. This is the volume of spherical shell as it is calculated here. Now when you are multiplying it, you will get radial probability. And if you want to get density, you have to divide this total term with 4 pi r dr square, 4 pi r square dr. So when you are dividing it by 4 pi r square dr, you are left with only this term, which is radial probability density. So radial probability divided by volume of spherical shell is radial probability density. So this 4 pi r square and capital R square, it is also known as radial distribution function. It gives you the idea about the distribution of electron density at a radial distance around the nucleus without considering direction or angle. Because direction and angle, it is all related to angular part, angular component of wave function. But we have not said anything about the angular component. We are just talking about the radial component. So that is why it will give you the idea about the distribution of electron density at a radial distance around the nucleus. But remember, it is not considering the direction or angle. Okay. Here we will see some graphs. So first consider a single electron of hydrogen atom in ground state, low energy state, having quantum number, principal quantum number 1, L is 0. That means it is nothing but 1s orbital, the simplest one. So for this orbital, we have taken distance in x-axis, and in the y-axis there is 4 pi r square psi square. Now it is basically analog of 4 pi r square capital R square, because in the previous slide you have seen 4 pi r square then capital R square. This is basically radial probability or radial distribution function. Remember this point, this is radial distribution function. So sometimes you will see in problem it can be mentioned as 4 pi r square capital R square or 4 pi r square psi square, but as it is talking about radial distribution function, so basically though it is mentioned here psi in this picture, but actually it is talking about only the radial part. So it can be expressed like this or 4 pi r square psi square, that is a total wave function. But in the total wave function, it is only considering the radial part. So that is why you can also write it as 4 pi r square capital R square. So now in this graph, we will see how this radial distribution function, it is changing. Its value is changing with distance smaller. So this is plot of 4 pi r square psi square versus r for 1s orbital. So as you can see, it is starting from 0 and there is a maxima you can get. If you draw a line, you will get value somewhere here, which is around half of 1 angstrom. That means it is around 0.5 angstrom, where we are getting the maximum point. So this is basically from this graph, it is giving you the idea about the maximum probability, which is basically occurring at 0.5 angstrom. It is also known as Bohr radius from the nucleus. So it indicates that the maximum probability of finding the electron around the nucleus is present at this particular distance, which is 0.5 angstrom. This information you can get from this picture. Similarly, when it is n equal to 2, L equal to 0, it is basically 2s orbital. And now you can see the picture is different. For 2s orbital, there are two humps. The second hump, it is having maximum somewhere here. So it looks different. But if you want to know that how to understand what will be the nature of the plot, that we will see not in this class, in the next class probably. We will see that how to know what will be the nature of the graph. That is when it will touch 0. Basically this point where it is touching 0 value of this 4 pi r square psi square, these points are known as node. So when you if it is node, you have seen that in 1s there is basically no such, there are not two hump, only one hump is there, so no question of node. Okay, but here you can see we are getting a node, and how to get node, when you will not get node, all this we will see later. But here the important point is, one is it looks like this, and 2s orbital it is different. Okay, so here the maximum it is for the second hump. Here you don't think it is 7 because it is here also this point is maximum, but this is higher, right? So this is for 2s orbital. Similarly, here we also have 3s orbital. Now there are total 3 hump, and this is the maximum point, right? Now 1s, 2s, 3s, you have seen all of these, and if we present it together, it will be like this. So here the red line is for 1s, only one hump is there, no node. Then we have 2s, which is the blue line, and the 3s, which is the green line. So all these three you can compare together. Next we'll see how it is for 3p. So for 3p it is, you can find some similarity with 2s, and there are two hump. One point is there which is touching this 0. Then we also have this picture which is 3D. Okay, so for 3D there is only one hump. There is some similarity with 1s, but obviously it is not exactly same. There is difference, and we are not getting any node. Okay, so how to know this nature, obviously we'll see in next class. So how these nodes you can understand, I will not start it because it will take time. How to understand how many nodes will be there, that we'll discuss in the next class. So in the in start of the class, I have already said that we'll discuss topics, angular node for p and d orbitals, shape of orbitals, but those two topics, because of lack of time, we have not discussed. We are just ending the discussion at radial distribution function. Okay, information related to nodes and shape of orbitals will be discussed in the next class. So we are ending here. Thank you for listening.